All right. Then, yeah, good afternoon from the Netherlands. Thank you very much for having me at this Best of CVPR session. My name is Daan de Geus. I am an assistant professor in the Netherlands at the Eindhoven University of Technology. And I will be presenting our work called Your ViT is secretly also a video segmentation model. And actually, this talk will be more like a tale of two papers in a way, because to understand our most recent paper, I kind of first need to introduce our paper from CVPR last year. So I will be taking you through that first to hopefully make you understand it a little bit better. So as the title suggests, this paper focuses on the task of visual segmentation. And in case you're not familiar with that task, it's that given a particular visual input, the objective is to produce for each region of interest a per pixel segmentation mask, such as this purple mask over here, or this gray mask over here, our corresponding class label, for instance, that this is a bed, that this is a wall, that this mask is the floor, etc. And I'm purposely keeping it a bit vague with visual input, because in this case, I refer to both images and video. And this talk will also cover both of these aspects. Now, this talk will be about visual segmentation, but hopefully the conclusions that we draw will also be more generally applicable beyond visual segmentation. So let's see about that. So one of the examples of what a visual segmentation task could be is image panoptic segmentation. In this case, the input is a single still image, and the desired output is a segmentation mask and a class label for each individual foreground object, such as the individual cars over here, or background regions. So for countable objects, such as cars, we distinguish between individual instances, and for the background, such as the sky or the roads, we just have a segmentation mask for an entire class. Now, another task that could fall under this category is video instance segmentation. In this case, the input is not a single frame or a single image, but a set of video frames. And in this case, we want to predict a mask and a class label per object across frames. And we want to keep them consistent so that we can re-identify the object that we identified in the previous frames and effectively apply tracking. And these are the two tasks that we'll also see throughout this presentation. Now, as I mentioned, this is a sort of a tale of two papers. And the first of these papers is Your ViT is secretly an image segmentation model, which we presented last year at CVPR, which was led by Tommy in collaboration with Nicolo, Alex, Nargis, Giuseppe, Bastian, Gijs, and myself. And this was a collaboration between us at the Eindhoven University of Technology and Politecnico di Torino and RWTH Aachen University. And in this work, as the title suggests, we focused on the image segmentation task. And we started, as you would always do, by doing literature research and looking, okay, what currently does the state of the art for image segmentation look like? And we found that it looks something like this. Now, you don't need to know all the details about this architecture, but as you can see, it's relatively complex. It consists of various components. We have a vision transformer that extracts the features. Then we have an adapter, which consists of convolutional layers, which injects and extracts features from the vision transformer and merges these with CNN features to then output multi-scale, multi-resolution features. And it does so to introduce some additional inductive biases that the vision transformer doesn't have natively. And then following that, we have a pixel decoder, which consists of deformable attention operations to sort of aggregate and combine all these features into a set of coherent multi-scale features that are then fed to a transformer decoder, which does the actual segmentation by taking a set of learnable queries and letting each of these learnable queries represent an individual object. And then for each of these learnable queries, it predicts a mask and a class label. So as you can see, this architecture is quite complex, and it has many of these task-specific components. And although these architectures are very accurate, they lead to very accurate results, they're also very inefficient because they're all sort of non-standard operations, and they introduce several bottlenecks at several stages. So in the end, these models are quite slow. So we were thinking it must be possible to do this more efficiently. So our hypothesis was that all of these complex components that were added on top of the vision transformer actually become redundant when the vision transformer becomes sufficiently large and when it's pre-trained with sufficient data and with proper pre-training objectives. And we think that this is the case because all of these added components kind of add these additional inductive biases in the architecture. And we think that a sufficiently scaled vision transformer actually learns all these inductive biases by itself. It no longer needs these additional components. So in other words, we think that a large pre-trained vision transformer is sufficient to do image segmentation. So what we do is exactly that. We take this state-of-the-art method, and we gradually remove these complex components to improve the efficiency, while of course attempting to keep the accuracy as similar as possible to the baseline that we have. So this is exactly what we do. So we start with this baseline that I've just shown you, and we basically compute several metrics. So we have the PQ, which is the panoptic quality, which is the standard accuracy metric for panoptic segmentation. We report several efficiency-related metrics like the number of parameters, the flops, and most importantly, the speed of the model in frames per second. Now, this is what we get if we run the baseline. The absolute numbers don't really matter that much. It's all about the relative numbers that I'll show you. So the first thing that we do is we basically get rid of this adapter here. As I mentioned, it consists of some convolutional layers, and it injects and extracts some features, and it's basically meant to introduce some additional inductive biases, which we think are no longer necessary anymore if we scale this up. So we do this, that's important to mention, in combination with a Dyno V2 pre-trained vision transformer. And if we remove this adapter and instead just create multi-scale features by downscaling and upscaling the outputs of the vision transformer, we see that the panoptic quality basically remains unchanged. It drops with a very small margin, but is not really significant. At the same time, the speed in frames per second does increase by roughly 25%. So this tells us that we're on the right track, and we're going to get rid of even more of these components. So the next thing we get rid of is this pixel decoder that we see over here. As I mentioned, it's used to sort of aggregate and combine all these features and consolidate them. But since they're now basically all from the same source, the output of the vision transformer, but then in downscaled and upscaled formats, we think this is no longer necessary. So what we do, we simply get rid of this module. And we see that once again, this doesn't really impact the panoptic quality at all, but we do see a significant speed boost in frames per second. And now the model is twice as fast as the baseline was. And this is mostly due to the fact that the deformable attention operations that this pixel decoder had are just not very efficient. So we now get rid of them. Now, the next thing that we do, we also get rid of some of these multi-scale features because we figured they're just down and upscaled versions of itself. They don't really add much new information. And we only keep the upscaled features for the high resolution features that we need for the mask calculation. And by doing that, we also get a small efficiency boost and basically no impact on the panoptic quality whatsoever. So now we've removed a bunch of components already, and we're left with two modules. And these modules, interestingly, are both transformers. They both just consist of attention operations and some MLPs. And specifically, in the vision transformer, what it does is, of course, it contains several self-attention layers between the image tokens. In this transformer decoder, on the other hand, we have cross-attention between these learnable queries and the image tokens to extract information from the image features into the token and into the queries. And there's also self-attention between the queries. Now, we thought, can we not just consolidate this into a single transformer that does all of these operations in parallel, that does everything jointly? So this is exactly the idea. So we just use a single vision transformer encoder that not only takes the image as input, but also these learnable queries and jointly processes the image tokens and the queries. Now you may be wondering, how do we do this exactly? And I'll take you through it. So in the beginning, EoMT, which is our encoder-only mask transformer, which is how we call it, works the same as any regular vision transformer. So we take an input image, divide it into patches, and then linearly project each of these patches into a patch token. So far, this is all standards. The next part is also standard, where we add a positional encoding, and we apply the first L1 encoder blocks in practice for a ViT large. This is the first 20 out of 24 encoder blocks. Now, after this 20th block, something interesting happens. At that point, we take the patch tokens and we concatenate the learnable queries to it, so that we now have one larger set of tokens that we then feed through the remaining encoder blocks in this vision transformer, in which, of course, the model applies self-attention between all of these tokens. So now in this encoder block, we not only have self-attention between the patch tokens, but we also have self-attention between the queries. We have attention between the queries and the patch tokens, and we have attention between the patch tokens and the queries. So in this encoder block, we have all of these attention operations that were previously separate in the encoder and the decoder, now all jointly together in a much more efficient way. And for this, we simply reuse the encoder blocks of the vision transformer. So no new operations, we just initialize these with the weights from Dyno V2, and then we fine-tune them for segmentation. Now at the output then, we have this set of tokens, which we then again split up to make the segmentation predictions. And as I mentioned, each of these queries learns to represent a single object. So for each of these queries, we individually predict a class label and a segmentation mask. The class label we generate by just applying a linear layer on top of each query. And the segmentation mask we generate by first applying an MLP to each query and then taking the dot product between that and the upscaled image features. And that's all that you need to do for segmentation with a vision transformer encoder. Now, how about the results? We've seen this table before, right? So before we had step 0 to 3, and now in step 4, we also remove the transformer decoder and end up with our EoMT. Now, in this case, as you can see, if we focus on efficiency in frames per second, we see again a substantial improvement. Once again, our model is twice as fast as the step before, and now overall, we have a speed up that is 4 times as large. We have a speed up of over 4 times. So the speed is 4 times as large as what it was before. At the same time, the accuracy is hardly impacted at all. Of course, we see a small drop of like 1.1 PQ, but this is negligible compared to the big speed up that we get. And we do experiments with different sizes of backbones. And we find that the larger the backbone, the smaller the gap becomes between this ViT adapter mass to former baseline and our EoMT model on the other hand. And if we scale this up all the way to a ViT 7 billion, then this gap completely disappears. So at that point, we're still twice as fast, but with the same accuracy. And this also sort of supports our hypothesis that we think that the model needs to have a large capacity to learn these inductive biases itself and no longer be dependent on the decoders that we apply on top. Now, the same applies to the amount of pre-training, the strength of the pre-training, because as I mentioned, by default, we use Dyno V2 pre-training, which at the time was the strongest that worked. And at that pre-training level, the gap was only 1.1 for panoptic quality. But if we used supervised ImageNet 1K pre-training instead, the panoptic quality drop increased a lot to 6.1. So this goes to show that the strong pre-training is really necessary to allow the model to not require any of these inductive biases from the decoders on top. So sort of the midterm conclusion before I go to our most recent paper is that we find that task-specific components, at least for image segmentation, but I'm pretty sure that this also applies to other tasks and other domains, become increasingly redundant at scale, and specifically pre-training scale and model size. And we show that by removing them and just using an encoder-only mass transformer, we obtain a very simple architecture that achieves still a high accuracy, almost as high as the state-of-the-art, while being over 4 times faster. So sort of the takeaway here, and I'm hoping that this sort of applies beyond image segmentation, is that scaling up the vision transformer is more effective than adding architectural complexity. Of course, this is very much in line with the bitter lesson, so we're definitely not the first ones to find something like this, but yeah, this really supports that hypothesis and that idea. Now you may be wondering, as the title was about video, how about video? Because so far we only showed this for image segmentation. Well, this is exactly what our CVPR 2026 paper is about. So not very creatively, we called that paper, Your ViT is secretly also a video segmentation model. In this case, this paper was led by Nargis and was a collaboration with Idil, Nicolo, Tommy, Bastiaan, Gijs, and myself again. And again, this was a collaboration between us and RWTH Aachen University in Germany. And very similarly to what we did for EoMT, we looked at, okay, what currently does the state of the art look like for online video segmentation? So for this video segmentation task that I showed before. Now, unsurprisingly, the architecture looked even worse because the task is more complex. So the architectures also will become more complex. So once again, there was a very inefficient, complex architecture. So hopefully you will remember this part of the architecture. So this is exactly the same as the image segmentation architecture that we saw before. But now on top of it, we also have various tracking specific components. So what these models do in a nutshell is they first apply per image segmentation, and then they apply a tracker to take the predictions from adjacent frames and match them to each other. So to identify which of the predictions in frame t-0 correspond to the predictions in t, to, of course, make some temporal correspondence and to be able to do tracking. And again, to do this, they introduced some new complex components like another feature extractor, some re-identification layers, which increased the training complexity, but also the model complexity, and another transformer decoder that combines the outputs from different time steps. So again, maybe unsurprisingly, we had a very similar hypothesis that these tracking components also become redundant when using large pre-trained vision transformers. And we think that this is the case because, yeah, the only thing that these video segmentation tasks require beyond image segmentation is that we need to do re-identification of objects between adjacent frames. And empirically, we found that pre-trained vision transformers like DynoV2, if you feed them two images, taken at different locations, but with the same object, then they produce very similar features for this object, allowing us to basically re-identify this object. And this re-identification is exactly what we need for video segmentation. So therefore, we think that the vision transformer itself is also really well equipped already to do this re-identification and to do video segmentation. So again, video segmentation, we think, can be done just as accurately with just a vision transformer encoder. So we do something very similar. We start from this baseline. In this case, this is KVIS. And we, in this case, report accuracy in terms of AP, average precision. And again, we have some efficiency statistics, number of parameters, flops, and frames per second. And of course, the first thing that is fair to do, which isn't really our contribution for this new paper, is to take this complex segmenter and replace it with EoMT, because this is just plug and play. So of course, this is the first thing that we need to do. And we find that, again, if we just plug this in for this framework, we get a significant speed up. So the speed changes from 15 frames per second to 42 frames per second, so almost a 3x speed up, while the accuracy stays roughly the same. So once again, we can just plug in EoMT and it works quite well. Now, at this point, of course, there are still some pretty complex tracking specific components on top of EoMT, such as this context-aware feature extractor and these re-identification layers. And I won't go through all the details, but we find that once again, if we remove these individually, that we basically have very little impact on the accuracy while getting a bit of an efficiency boost. But then still we're left with this sort of transformer decoder that combines information from time step t-1 with the information from the current time step t in order to do this tracking. So we thought, again, since both of these use transformers, we can just integrate all of these capabilities into this vision transformer encoder. So what we do is we start with EoMT and we extend it to also be able to support video segmentation. So And when I mean we start with EoMT, I mean this very literally, because for the first frame, the prediction that we make is just identical to what we would do for EoMT. Because in the first frame, of course, there's no previous predictions yet, so there's no tracking that we need to do or even can do. So we only need to segment the new objects that are present in this first frame. So we just apply EoMT as is. We compute the patch tokens. We take the learnable queries, concatenate them with the patch tokens, and then process them to finally produce the class and mask logits. Now, for time step t is 1, which is the time step that follows afterwards, now things become a bit more interesting, of course, because now we no longer need to identify any new objects, but we need to segment objects that were present already in the previous frame. So what we do is we take the output queries that EoMT produces for the first time step, and these queries, if you remember, all represent one object. So for instance, this represents car 1, this one represents car 2, etc. And we take these and we instead feed these queries into EoMT for the next stage. So we basically tell it, okay, this is information about a particular object. Find it for me in this new frame. So we ask the model to sort of find these objects, re-identify them, and produce the class and mask for this particular object. And then if we find that, then of course we take these queries and then we feed it to the model for the next frame, and we can unroll this indefinitely. So this is what we call query propagation between frames. Now, here we have the table again. I grayed out some parts that I mentioned before that are super relevant to the story. But so from EoMT, where we just apply it naively without any temporal information, surprisingly, this already works quite well. So it turns out that even without specific temporal modeling, the model can kind of learn already which of the tokens should be, or which of the queries should be representing which object. But with query propagation, we see that the performance improves a little bit beyond what we had before with EoMT. At the same time, the speed is significantly faster. So if we now compare this 162 FPS to this 42 FPS, this is another 4 times speed up, and the overall speed up is over 10, a factor of over 10. So this is really a huge speed improvement. But of course, in this configuration of the model, yeah, we still underperform this baseline quite significantly by 5 points in the average precision. And of course, we weren't satisfied with this, so we looked into why this happens. And we found that while the model is pretty well able to track objects and re-identify ones that are already previously identified, it sort of loses the capability to identify any new objects because it's only looking for objects that it's already seen before. So for this, we also present a very simple and efficient solution. So in addition to these queries from the previous frame, which we call track queries, we also condition the model on the learnable queries. And we don't just concatenate them, which would, of course, increase the computational effort, but we just add them together with a very simple linear operation and element-wise addition. So in this case, if we then feed this to the model can sort of decide itself whether it wants to identify an object that it's already seen before with a particular query, or whether it wants to spend this query on a new object that it hasn't seen before. And by just feeding this to the model without giving it any information about what it should do with it, the model can learn to figure this out itself. And this is also exactly what we see. So the resulting model is VidEoMT or VidEoMT. And with this query fusion, where we add these learnable queries to the track queries, we almost completely close the gap between us and this Cavis baseline. So now we have an average precision that's almost exactly the same. The speed remains almost unchanged with respect to this super efficient configuration. And we are still over 10 times as fast as the baseline while having the same accuracy. And this is all enabled by the fact that we no longer have all these task-specific components which have operations for which the hardware or the software isn't optimized. And we now really only have a transformer-based model, which the GPUs currently, like the NVIDIA H100 and flash attention and everything, can handle very, very well. So everything's optimized towards this. And this is really what gives us this boost over the baseline. Once again, we try this for different model sizes, and we see that consistently we are over 10 times faster than this baseline. So this is the baseline that we have, which operates roughly at 20 FPS, even for like the small model. It's just bottlenecked by these components that we add on top of the backbone. Whereas for us, we can reach speeds on an NVIDIA H100 of 160 FPS up to 320 FPS. So this is really quite fast. These are some examples. This is just something that honestly I did cherry pick because it looks quite nice, but you can see there's some occlusions which the model can handle quite well. But I think it's just a nice example to show. But overall, what we can conclude, both from EoMT and now from the video extension of it, is that scaling up models, and particularly the encoder and the pre-training of this encoder, allows us to simplify the rest of the model, because the inductive biases that you may want to add with components that you add on top of the encoder simply become redundant or unnecessary. And that this simplification that you then end up with really boosts efficiency and hardware compatibility, because you only have transformer operations, for instance, for which a lot of hardware and software is just optimized much better. So I hope that this was interesting, that it maybe gave you some new insights, and I'm pretty sure that this also generalizes to other tasks. And of course, if you're interested in using our work, all code and models are all available. It's also integrated in Hugging Face already. So yeah, try it out. And if you have any questions, I'd be more than happy to answer them. Thank you.